All right, so we're down to the next bit here. So this is going to be a little bit of cryptography. Cryptography is awesome stuff and very interesting. I teach whole workshops in cryptography, and it's very exciting stuff. It changes really fast. You would think it wouldn't like math, but it doesn't. It changes really fast. And then we'll have some perimeter defenses and environmental controls. So here's the basic cryptography concepts. Cryptography is secret writing, and cryptanalysis is using mathematics to break cryptography. And so the way you test a cryptographic system is through cryptanalysis from a mathematician's point of view. There's another way to break a cryptographic system, which is what we've already talked about before, which is you attack the implementation of it in hardware with an attack like a side channel attack, and that is not directly attacking the cryptography. So the current state of the art is the mathematics of cryptography is very advanced, and the standard systems are very, very good. So the mathematics is strong. The problem is when you actually implement it, you make mistakes, and the main mistakes you make are in key handling. You have this secret key, and somehow you have to not let the bad guy get it, but you have to not lose it either. So you have to have a backup somewhere, and an incredible number of people do something foolish with the key. And then, of course, that beautiful math doesn't save you. So a cipher is the algorithm, and plain text is the message before you encrypt it, and then you turn it into ciphertext. And the idea is that the ciphertext is so scrambled that nobody can deduce the plain text without the key. That is the goal you attempt to achieve by having a strong cryptographic system. So confidentiality is the main thing you get out of this. That's the main product of cryptography, is that unauthorized people don't have the key and they can't read the message. There's also some integrity provided in that a cryptographic message usually cannot be altered by someone who does not possess the key, although there are quite a few attacks that violate that. Existential forgery attacks and padding oracle attacks involve altering encrypted messages even without having the key. This turns out to be possible in a few important cases. So authentication is knowing who somebody is, not just that they claim to be someone, but they have proven it somehow by knowledge of something like a password or a fingerprint. Non-repudiation is assurance that your record, your log, is correct. And therefore, when my log says that Joe did something, that means Joe really did it, and he can't lie and tell me he didn't do it. That's what you want. Confusion means that there should be no relationship between the plain text and the ciphertext. So if the ciphertext gets, if I change one letter of the plain text, it should change all the letters of the ciphertext, not just one. There shouldn't be a simple correlation between them. And diffusion means they should be dispersed throughout the ciphertext. These are desirable cryptographic properties. The basic rule is that if there's a pattern in the input, there should be no pattern in the output. Ciphertext should be white, which means it should have a 50% chance of every bit being 1 or 0. It should be totally free of patterns and content. There shouldn't be any pattern in the encrypted stuff, because if there is, you can use that pattern to deduce something about the key. So substitution provides confusion. This replaces one letter with another in the simplest case, and permutation, it rearranges the letter. That provides diffusion. So strong encryption means that in practice, people that don't have the key cannot read the plain text, and a work factor is how you measure it. You can calculate how long it would take someone to crack it, given a cracking technique, and then you can decide how much time or money or processing power you think your adversary has, and then make sure that the work factor is much larger than that, and then you feel like you have a sufficiently strong cryptographic system. One common technique is secrecy, where you try to hide your system. Many companies market products and they will not tell you what cryptography they're using. Almost every professional will refuse to buy a product like that. It is almost always the case that the secret system is something stupid and easily broken. An incredible number of people think they can just make up a cryptographic system in the shower and it will be strong. They go, oh, I'll shift every letter to the left and then add 1 to every binary bit and that'll fix it. It turns out that this has all been solved centuries ago by mathematicians. Anything you think of in the shower has been cracked centuries ago by somebody. There's only a few ways to do it, and they have been carefully researched by the smartest people in the world. And the rest of us, unless you are one of the 10 smartest people on earth, you should not attempt to create cryptography at all. You should just use a standard system. The people that wrote it have really worked hard on it. You just take one of the standard systems like AES or RSA and just learn to implement it correctly. So monoalphabetic systems change each letter to one other letter. This is what you see in the Sunday morning cartoons. They have cartoons with scrambled letters, and little children can solve them. The A goes to X, and the B goes to Y, and the C goes to Z or something. That's the Caesar cipher, and there's ones that just do it randomly. Those are trivial to break because of frequency analysis. You can just look for, say, one-letter words. That's got to be I or A. You can look at two-letter words. They have to be as or so or something. You can pretty soon just guess it. If not, all else fails, you can just count the frequency of the letters. E is the most common letter by far. The next one is T, so you can only have a couple of options. The first most popular one is either E or T, and the next one is either E or T, and you can pretty soon find a the, and then you know which one is which. And this kind of system can break in really fast. Polyalphabetic ciphers try to prevent this by having a system where the first letter uses one substitution, the next letter uses another, the next letter uses another, so there are multiple possible replacements for the same letter to make frequency analysis less effective. All cryptographic systems use modular arithmetic, which is pretty strange at first. It's like what you have on the clock. A clock goes from 1 to 12, and if you add one more, you're back to 1. There is no 13, or if you want to look at it, there is a 13, but 13 is equal to 1. So this is modular arithmetic. And you typically start at 0 for cryptography. The point is, you have some input data like letters or say bytes. You have ASCII, so it only goes from 0 to 127, and if you want to include the non-printable characters, it goes 0 to 255. That's your input. You want to encrypt it, and you want the encryption to still be in that range. So you don't multiply it by something and let it get bigger. You use modular arithmetic. So when you encrypt it, it still stays in the same range. And all cryptography uses modular arithmetic. Another thing they use is exclusive OR, of course. So 2 bits, if they are the same, you have 0, and if they're different, you have 1. You do not use or and because that would not be white. If you use and 1 and 1 is 1, 1 and 0 is 1, and 0 and 1 is 1. So if you had data that was half zeros and half ones, and you ANDed it with a key that was half zeros and half ones, the output would be 3/4 ones and 1/4 0. Now that might sound okay, but it's not, because Shannon entropy calculates the amount of information contained. You have destroyed information. Something that is half ones and half zeros has the maximum amount of information. Something that's all zeros or all ones contains almost no information. Something that's 3/4 ones and 1/4 0 does not contain as much information. So if you run it through a cryptographic transformation that is not white, you cannot reverse it because it loses information. So you have to use transformations like this that do not change the proportion of ones and zeros. So XOR reverses itself. You can XOR attack at dawn with apple, 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 and you get this garbage with $signs. And if you XOR it again with apple, apple, you get attack at dawn. That's a lot of cryptographic systems undo themselves. So repeating cryptography multiple times does not necessarily make it stronger, and sometimes it just undoes itself. So you got to have data at rest encrypted. Now, whole disk encryption only protects computers when they're turned off. But one common thing people do is they talk about encrypting servers. And this doesn't make any sense because the server is always on. And therefore, since it's on, it's got the encryption key in RAM and it's decrypting the data on the hard drive. And the attacks that are you're going to come in over the network and put malware on it or something, and they're going to get the data. Encrypting the disk doesn't do any good unless it's turned off. Data in motion is what you have on the server while the machine is on. That's data moving from place to place over the network. So you want things like VPNs and HTTPS and WPA to encrypt it while it moves over networks so that people that sniff on the network traffic can't read it. So protocol governance is deciding what protocols you should be using, and you've got to consider options. The cost and the speed and the strength is how cryptographically strong is it, whether your adversary could reasonably break into it. So there's a few codes about this, and then more coming. 4B1 is here. Okay. Yeah. This is a very good question. Now's the time. I'm going to put it here so it's on the video. So I got hacked at DEF CON because I went to DEF CON and I used Gmail. And I said, it's HTTPS, I'll be fine. This was about 2010. And what I didn't know was at that time, Gmail used HTTPS for the login process, which was better than a lot of people. But after you logged in, it went to HTTP and identified you with a cookie sent without encryption. And I did not know that. And so they stole my cookie and got in my account and put me on the wall of sheep. At DEF CON, they humiliate you if you get in your account by putting your name on the wall of sheep, and I was on the wall of sheep. And after that, I went and showed everybody this. So HTTPS didn't save me, but in order to fix that, Google switched to 100% HTTPS. So if you were to go to an untrusted public network and log into Google with HTTPS, you would have that layer of encryption. And so you might think you'd be okay, but there are attacks on HTTPS. If I'm a nation state, for example, China does this frequently. They can send BGP packets over the network, and they did it again yesterday, or some other company did, where they reroute global traffic to go to the wrong place. And China has done this many times, where for about a half hour, they take American traffic and run it through China. And then they could sign it with a fake certificate. And the Chinese government is trusted as a certificate authority. Now, this is a fundamental problem. The certificate authorities are trusted. And if you don't trust China, then no Chinese websites would work. So you have to add them to the trusted list, but you don't really want to trust them too much. And so there's a problem with this binary system, trusted or untrusted. So Chrome has implemented a system where they know who should be signing the top 1,000 websites. And there's also now I think it's HTTP key pinning, STS, strict transport security headers are turned on for Google. So if you're using a modern browser, it will memorize the certificate authority the first time it goes to a site and then not let it change and warn you. And that's an attempt to fix that. So that will help fix the problem of where you actually get a legitimate certificate from a trusted authority that's wrong. There's another attack, SSL strip, where I run a proxy that connects to Google over HTTPS and serves it to you over HTTP. Now I can get in and your browser will be fooled unless it's a browser that knows that Google should be HTTPS, like Chrome. So that would probably get you if you're using a browser like Internet Explorer or something. There is another attack that's even nastier, which, well, another way to get into that attack, there's a very common situation, and last I checked, Salesforce was doing this. Yeah, here's Salesforce. Let me turn on developer tools. View, tools, web developer. Okay, web console. Okay, I want the network console, and I want to preserve logs. There. Okay, preserve logs. Okay, now I want to go to salesforce.com. And I want to go to http salesforce.com. Okay. And unless they've updated it, which I highly doubt, it's going to do this. Okay. Yep. Okay, it did a get to http salesforce.com without the padlock. And they got a the response here. I'm not seeing the response. They should be somewhere. Here's the response. Response, okay, and the response is something like a 307 redirect, which somehow is not showing up here. But the point is, they do listen on port 80. They let you come in with HTTP, then they redirect you to HTTPS. This is a terrible security practice, and almost every company does this. For some reason, companies believe that people are using devices that only speak HTTP at first. I don't know what they think people are using. MS-DOS-based browsers or something. And so they think that they have to do this because people are coming with HTTP and then you redirect them to HTTPS. But the point is, I could just hijack it at this point. When you request the HTTP page, I could just serve it to you over HTTP. And your browser would not know anything's wrong. And then I could get it over HTTPS and now I can get your data. So if you really have HTTPS working, it's a layer of protection, but there are attacks. And so if you use a VPN, you have another layer of protection under your control, and therefore you're a lot safer. So I tell students, oh, I don't bother VPNs, it's not worth the bother. And I said, did you ever get hacked? And I said, well, as a matter of fact, I did get hacked. And if I'd been using the VPN, I wouldn't have. So maybe I should stop saying they're not any good. And now I got one and use them because I started going to China and I have to keep getting through the Great Firewall. And then I found out how great it is to get around all the idiotic content filtering. Everywhere I go, they're blocking stuff I want to use, and VPNs blast that away. That's the main reason I use them now. because I go to coffee houses and they're blocking stuff, and I'm fed up with my college blocks everything. And after a while, you get in the habit, it's really pretty nice to use a VPN. Yeah. This is Firefox Developer Tools. Chrome has it too. You open Developer Tools and you have all these interesting things, and you can watch web pages load, and you can diagnose how they load, and they give you this timeline too, so you can figure out what part of the page is making it slow. It's really very useful. Yeah. Yes. Yes, it does. Here, I'm glad you bring that up. Let's do that too. You can see it in Wireshark. So let's open an HTTPS connection and watch the packets. I'm going to start sniffing. Capture options. That's fine. Ethernet. Okay, start. So now it's sniffing. Now I'm going to open a page like, let's do Salesforce.com again. That's fine. Okay. So there's Salesforce.com. Okay. And here's a lot of packets. Okay, so let's find out what happened here. Now, I got all kinds of junk here I don't want to see. I'm going to start with DNS. Okay, here's the DNS resolutions. And so someplace in here will be Salesforce. And if this bothers, there we are, Salesforce. So this is where it all starts. I try to find Salesforce. I ask a DNS query. Now, this is a huge privacy risk on the internet. DNS queries are in plain text, unauthenticated. We're slowly moving to DOE, DNS over HTTPS. But most people aren't using it yet, and clearly this college is not using it yet. So the DNS query finds the address of Salesforce. So this is where it starts at packet 281. So now I'm going to quit filtering and look at the packets after 281. So here's the DNS query. It asks where Salesforce is, and it gets an answer, a response here. And the response says, it is at 9543 something. So I want to look at the traffic to 9643. So now it connects to the server. So here we go. 9643. This is a SYN sent to the server. Then the server will send back a SYN ACK. This is, I send a SYN to the server. Then I should see something from 96. Oh, let's just do this. I'm just going to right click and follow the TCP stream. That should be easier. There we go. Okay. So here's the stuff going to the server and back. And now if I close it, I should be able to see the start. Here we are, SYN, SYNAC, ACK. So that's the TCP handshake. So what that does, that doesn't provide any encryption yet. It provides addressing and a socket. So I have an IP address and a port number at that end, and have IP address and port number at my end. So with those 4 numbers, I can now send data both ways that will not be mixed with anybody else's data. So I have a direct connection between my browser process and their server process, but it's not encrypted. It's not a VPN. But it is a virtual channel. So now I've got that. Now I send a client hello to the server, which is initiating a TLS connection. Now it cannot be encrypted yet because I don't have a key yet. So the client hello tells the browser, I am trying to start Secure Sockets layer. And Secure Sockets layer is in fact obsolete. It's really TLS, the modern version, TLS version 1.2. And here's the client hello. And the client hello tells it, here's what I can do. My browser can handle these systems of cryptography. This is Firefox, and it's fully updated, so it's got a lot of good choices down here, SHA-256 and AES 128, and a bunch, and here's even probably got DES for crying out loud. Anyway, it's got those 14 or 15 compression suites. So I can speak those cryptography systems. So then the server replies, and the server tells you which one we're going to use. The server changes Cipher spec and picks one of them and says, we're going to use this one, which I think is down here someplace. I'm not sure I'm in the right place, but someplace in here, it's going to say, here's the one it picked, TLS, Diffie-Hellman, RSA with AES 256, Galois counter mode, SHA-384. That's a pretty modern one with everything long. So I offered it 14, the server picked one, and now we go. Now, if I intercept the messages, which is possible because nothing is encrypted yet, I can lie to you. So if I'm in the middle, I can now lie to you, and the server can choose the weakest of your options. Now, if I can intercept your outgoing method, I can tell it, I can offer it something really weak. And then the server should not allow it. But a lot of people haven't updated their servers, so their servers, in fact, have old, obsolete, weak methods. And unfortunately, because of American cryptographic export restrictions, like the K and the N versions of Microsoft Windows have left, there's a large population of internet users that are using deliberately crippled operating systems that can only speak insecure encryption. So if you don't want to lose those customers, you have to support those crappy encryption methods. And now, if I'm in the middle, I can trick it into serving it up in an unsafe encryption method. There's another reason why a VPN would save you. Again, even if you are using HTTPS, at this point, I could cripple it and you would never know. Because I don't know a tool that would do this, but I could, in principle, negotiate a K method that's really weak with the server and then re-encrypt it with a strong one so your browser doesn't know I did that. And I don't see anything that would save you. So it's, this is the fundamental problem, is key distribution. Anyway, it's good to see there's like a 7-page handshake for the HTTPS. When it all works, the end result is I then get a digital certificate, which we saw before. So Salesforce gives me a certificate, and that certificate contains a private key, which we saw there, private review certificate. Here we are. And so the point of this is details to give me this private key, which is in here someplace. There we are, public key, the public key, pardon me. So there's the public key algorithm, RSA encryption, and here's the public key, 2048 bits. That was the point of it all. That is the public key, and when I scramble data with that public key, nobody on earth can read it but Salesforce, because they have the private key, and they don't have to transmit the private key to anyone ever. So everybody on earth uses the same public key, and it's all perfectly safe as long as they don't lose the private key, and as long as nobody finds a mathematical hole in this system. So it works very well, but nothing is perfect, and there are attacks. And a VPN would give me another layer of encryption, which would protect all these weak spots. It's just like any layered security. I now have 2 layers of security, so most of the attacks I described would not be able to do it, so it'd be much harder for the attacker. They would have to defeat that in addition. Nothing's ever perfect. If you really wanted to get in and you were the NSA, I'm sure you would blast through it all, but it's a lot harder. Good, I'm glad you brought it up, because this is just the kind of stuff. And let's see, I think if I can close some of my windows, I've got Cahoots underneath there somewhere.
1111. Do you think that's DNS is okay?
Well, yeah, it's just Cloudflare. It's another DNS server, and they do support some of the advanced things like DOH, and they claim to be privacy supporting. I don't know why they claim they're not going to hand over the logs or something. I mean, it's fine. I don't really understand why it's any better than anything else. But 8888, which is Google, is kind of nuts. I mean, because if you could see someone's DNS traffic, that's a lot of information. That's more information than from cookies. Now, Google promises they're not going to target ads with it. But I mean, there's a famous psychology experiment where they have kids and they put a plate of cookies here and they say, don't eat the cookies. And then they watch how long before they eat the cookies. And I can see Google, there's all this DNS traffic. It's worth $100 million, but don't. And how long can this go on? Everyone's just handing them every URL they go to. How long can they resist that? I don't see it. It wouldn't be illegal to take it. Whoever promised it has probably gone by now. Why aren't we taking it? At every board meeting, I'd be asking, look, you mean you're letting all this money just go away for nothing? What are you, nuts? Yeah, if I cared, yeah. Another one's OpenDNS is nice, 208.67.67. The thing about them is they'll block malware. So if you go to a malicious domain, they won't resolve it. So that's kind of nice. Yeah, they're all fine. It's good to know a few of these. If you use DOE, that protects you from the kind of sniffing I just did. That encrypts the traffic DNS over HTTPS so that you're, by the way, the purists hate DOE because it doesn't make any damn sense. DNS is at like layer 3 or layer 4 and HTTPS is at layer 7. So how can you put a layer, I mean, watch what happened here. First I had to do DNS resolution to get the IP address. Then I had to do TCP handshake. Then how can I do the DNS over HTTPS? I have to do a TCP handshake first to make up the HTTPS. So it kind of makes no sense, but in practice, it does make people safer because you do a unencrypted handshake early to get to your HTTPS provider. And then when I go to somewhere else, that's all encrypted. So it will make you safer, but it kind of violates the logic of protocols. And the purists don't like it. But in practice, it's the one that won. There were other things like DNS Curve and DNS Crypt that never got anywhere. So DOE is going to be it. DNS over HTTPS is going to be the privacy preserving DNS that everyone's going to start using. And now Cloudflare supports it and OpenDNS supports it. It'll pretty soon be built into browsers and operating systems. And we'll all be using it. And that'll probably be better. It'll be worse for network security, though, because one great way to secure a network is to run DNS monitoring. And it is awesome. All you have to do is monitor the DNS traffic, and you know everything everybody is doing and who they were. So if anybody in your company is doing whatever's forbidden, you know exactly who. I have students come to me and say, I'm the network administrator, and the boss tells me this guy is doing a bad thing, find him. And I said, just monitor DNS. And you'll have it right there. This IP address went to that website at this time. Bang, you're done. It's very handy, but of course that means it's terrible for privacy. So DOE is the improvement. Anyway.
You set that up over a Splunk, you analyze all the stuff.
Sure, or you can just use Wireshark. You can just use TCP dump. You can write a little Python script. It is so simple. So I mean, if your boss wants this, you can turn it on, and tomorrow you can have, I know exactly who did it and exactly where they went, exactly when they did it. Go fire this guy. It's great. It's like having a security camera over every desk. But, you know, that's nice for your network security staff, but other people get nervous about it. Anyway, all right, let's see what's happening here. I killed the music. There we are. Now I feel better. This is why a lot of strong, government states like Russia and United Arab Emirates will not let you do any encryption where they don't have the key. BlackBerry got in trouble. BlackBerry encrypted everything point to point to their servers in Canada, and United Arab Emirates said, no, you must put an endpoint in our country and break the encryption there so we can examine the traffic. And they did that because they lose the business. But it's a lot of governments have the same issue I'm describing. DNS, they want to see what you're doing. They do not want to let any encrypted tunnels go out. They want to open everything and see what it is. And the FBI wants to do it. And in America, they have less legal authority to force that than they do in other countries, but they keep trying to change that. They haven't succeeded yet, but they would like to spy on everything. There's a natural tension between the civil liberties and the law enforcement people. Anyway. So, a photo shows Jeff at a meeting, so he can't deny it. What does the photo provide? This was Jeff Sessions, in fact. One of the early Trump lies. Jeff Sessions claimed he wasn't at the meeting until they put on Twitter the photo of him at the meeting. Right. That's non-repudiation. Caesar moves each letter 3 steps in the alphabet. This was military-grade encryption 2,500 years ago. So what's that? Okay, that is substitution. Every letter is substituted with another according to a simple pattern. And that was unbreakable military security at that time, because when very few people could read at all, scrambling the letters enough was enough to be military-grade security. Not anymore, of course. Which systems resist frequency analysis? Polyalphabetic. All right. What's 17 mod 5? Mod 5 means the number goes from 0 to 4, and then they wrap around again. Okay, it's 2 modular arithmetic. You divide by the modulus and take the remainder. So 17 is 15 plus 2, because the numbers go from 0 to 4, and 5 is 0 again. So you can subtract 5, and it has no, that's how it works. So you divide by the modulus and keep the remainder. That's what modular arithmetic is. And all cryptographic systems are based on modular arithmetic. Or I mean, all the ones that are in common use. And that's why even the Caesar cipher, you go from A to Z, you shift them forward 3, and Z goes to ABC, you wrap around. You don't have some other letter. You stay within the set of possible letters, and the encrypted stuff is still within the set, so you have to be on the ring. Otherwise, it would go off the end. If you just were to like add 3, then your Z would turn into Z plus 3. You'd need another letter. And you don't want that, so you put everything on a ring. What's 3 XOR 4? Okay, it's 7. So let's talk about that. That was not a popular one. All right, so 3, that's easy. What's 3 in binary?
1, 1.
Right, 0, 1, 1. What's 4?
1, 0, 0.
So you just do it bit by bit. So 1, 0 XOR 1 is what? 1 XOR 0 is 1? 1. That's 7. That's how it works. You do bit by bit. Okay? If the bits are different, the answer is 1. If either one of them is 1, it's 1. If they were both 1, it would be 0. But 3 XOR 4 turns into 7. XOR is a very simple way to scramble things, and it is part. All these simple substitutions by themselves are far too weak and were cracked centuries ago, but real military-grade encryption uses these same processes just over and over again. You do an XOR, you do a substitute, you do a shift, then you do another XOR, a substitute, and a shift. You'll see even AES is just these same fundamental elements combined together in many cycles. These are the fundamental transformations that all encryption uses. All right. So, the history of cryptography, of course. One of the early ones was the Spartan Scytale. You would write your message and then you would wrap it around this stick and then you'd read it the other way. So all this did was skip the letters. So if the stick was like 5 letters around, you'd have every 5th letter, but you could even use a stick that was tapered and changed its size so it was different. And the point is, someone at the other end would have another stick the same shape. And you wrap it around that stick and read it. This is just transposition. You don't change any of the letters, you just put them in a different order. So that's one kind of encryption. The Caesar cipher moved everything a certain number in the alphabet. So the A turns into D, the B turns into E, and the Z turns into C, and so on. Everything just shifted forward 3 in the alphabet. The Vigenere cipher was a polyalphabetic substitution cipher. So you would encrypt E, T, you'd have a key, like a keyword repeated over and over, and the key would tell you which alphabet to use. So if you're using the alphabet E, T would turn into X. And so you'd have a keyword like apple, apple, apple here, and you would use the A to encrypt the first letter, and the P to encrypt the second letter, and the P to encrypt the third letter. That was how it worked. You had 2 things. You had a shift distance, like you had in Caesar. Well, that's included. What you have is a keyword that's repeated over and over. That's the Vigenere cipher. And it is, you still can crack it, by the way, with frequency analysis. If the key is like 5 letters long, that means that if E is the most common letter, there will be 5 peaks in the frequency. But anyway, it's much harder to crack. Here's a cipher disk, a modern cipher disk for the cryptology. This is the Captain Crunch decoder disk you get in a box of cereal when I was a kid. You just rotate the circle in the middle and you've got the Caesar cipher. The Confederates used this system. They had these metal things you carry around that did the same thing. You rotate it for a certain number of steps and you're getting the Caesar cipher. All right. Then there's the book cipher. The book cipher, you use a book like a Bible or any other book, and 2 people have the same book with exactly the same page numbers and everything. And then you just write down number, paragraph, word, and you pick words out of the book. And by looking them up, you can get it at the other end. And if somebody doesn't have the book, they can't get it. There's no pattern or math or anything. So this is a secret key system where it's all in the secret key. And unless somebody can guess what the book is, you're hosed. The running key cipher, you use a phrase or document as the key. So you have a document like the Constitution, we the people, is going to be your key. And so that is the key. And it's sort of like the book cipher. If people can't guess what your key is, they're never going to get in. So codebooks is another thing. They started out with telegraphs. To make telegraph signals cheaper, they would substitute long phrases with simple shorter phrases as a simple form of data compression. So they would have code names, and this is what the military does. They have code names for the family, like Barack Obama is Renegade, and Bill Clinton was Bubba. And I don't know what they have for Trump, but they have this sort of insulting, mocking trade. They use a code word for radio transmission for the president and their family to hopefully make it harder for people that want to attack them from figuring out who they are, although everybody needs to find out pretty soon anyway. Now, the one-time pad, this is why one common mistake among cryptography students is they think you need computers to make good encryption. Absolutely unbreakable encryption was developed centuries ago, and it's completely fine in a one-time pad. This is based on simple logic. If I have random letters and I fill up page after page of them and I give you that page, then you take every letter of mine and you look at that letter. If it's an A, you leave it alone. If it's a B, you shift it by 1. If it's a C, you shift it by 2. So if you use, the key has to be longer than the message, and you have to never reuse any part of the key. So if you want to encrypt one page of stuff, you use one page of key and then you throw it away and never use it again. If you do that, this is completely unbreakable. And there's a simple reason why it's unbreakable. Suppose you have a page of data that's been scrambled with a one-time pad. Now you can calculate, you brute force attack. You can take every possible series of letters and do it. And if you do, you will produce every possible output. So you will have every possible printed page, and one of them is right, and all the rest can contain perfectly readable data, and you have no way to tell which one is the right one. Most cryptographic systems based on mathematics have the property that the key, if it's right, it turns into English, and if it's wrong, it turns into garbage. So you can actually just look for the thing that is readable or the thing with lower entropy, and that'll be the one that wins. You can tell which one is right. But in this case, you will get every possible printed page as one of the possible outputs, and there's no way you can tell which one is right. And that has proven to be true. Nobody's found any way around it. If you have one-time pad, you will never get in. The only problem is key distribution, which is a huge problem. You have to securely deliver keys to the recipient that are longer than all the total messages you will ever send. So it's in practice very difficult to use. And so what people do in practice with like TLS is you cannot distribute a one-time pad, so you distribute a short key, and then you have a mathematical algorithm to generate something that looks random, that isn't really random from it, and you use that instead. And then it's not as secure, but it's much more usable. Well, there are a few one-time pad systems in commercial use, but in principle, they're very hard to use because delivering the key is a huge problem. And if you had some way to keep on delivering more and more keys securely all the time, then you don't need encryption at all. You could just send your messages that way. So it's rare to find a use case where this is practical. Or the KGB, what happens in practice, many governments have used this. What happens is, one thing fun about the one-time pad, and I gave my cryptography students a project like this, if you use it twice, it shatters like glass. It's amazing. How do you make a computer, you can crack data that's sent by using the same one-time pad even twice. It's amazingly bad. So, and a lot of people did this. The KGB had used them in the 40s in a war against Hitler. And they didn't have enough one-time pads. So instead of having the original protocol, you type it on a typewriter and have one piece of carbon paper, they started putting 4 and 5 pieces of carbon paper to make more copies of the same pad. And because they were using it more than once, they got hosed. It was too difficult to deliver the key, so they accelerated that process by making more copies of the key without understanding how much this collapses when you reuse the key. It's amazing. There's a simple running attack. What you do is you guess some of it, and then you get a few letters, and then you complete this word, and then you can guess this word, and then you complete this word, and pretty soon you can just sort of walk your way through it if you have 2 things that are encrypted with the same one-time pad. You would think it's not a big deal, but it is a big deal. It changes it from a perfect cipher to an easily cracked one. So there's these large manual typewriters that would do this. That's what Enigma had. There's a bunch of these where you type letters, and you dial a key in here, and there's a bunch of gears that will change the letter into some other letter. So they encrypt it, and at the other end, they have the similar machine to decrypt it. There were a bunch of these before computers. These were mechanical scramblers and unscramblers. And so then came laws. The Coordinating Committee for Multilateral Export Controls, the United States government's principle has always been that the NSA should have a backdoor into everything, but it should be no bus, is what they call it, nobody but us. There should be a way in, but nobody else can find it. And we should not give our enemies anything that we can't crack. So we should only export encryption that we can get into. And many times they've been caught lying to us and perverting the National Institute of Standards process into lying to us and telling us something is secure when it isn't, because their priority is that they should be able to get into it, to where the cryptographic community is probably among the most radical, leftist, angry, rebellious group that feels like you should never trust anything the government says, because unfortunately the government has totally lied to them over and over until they have a real sore attitude about it. I would like to say they're wrong, but the problem is they're not wrong. The government has totally lied about cryptography over and over. Anyway, so here's the types of cryptography that matter to us. There's a whole branch of mathematics, which is fine for mathematicians, but for us, for practical purposes, there's only 3 cryptographic things you want to do. Symmetric encryption is the main kind, where you scramble something with a key, and the other person has the same key to open it. Asymmetric encryption is where you have each of you makes a pair, public and private key pair, and you only distribute the public key, and you keep the private key secret. This solves the key distribution problem. The problem with symmetric encryption is you somehow have to deliver the key to the other person. And how are you going to do that, since the whole idea is you don't have a secure way to talk to the other person? Asymmetric encryption solves that. The public key is not secret. Everybody can have it. The only problem with this is one way. If you make a key pair, you can now receive secret information, but you can't send any information to anybody. This is why people got mad at Hillary Clinton for using unencrypted email. The problem is, if you're a high-tech nation like America and you want to send email to a low-tech nation, you can't send them encrypted email because they have to make a public-private key pair at the recipient's end. When Snowden wanted to leak NSA secrets to Glenn Greenwald, he wanted to use PGP, which the NSA cannot crack, apparently. And the problem is, he cannot send it without Glenn Greenwald making a private public key pair, and he couldn't get him to do it because he wasn't technical. He couldn't explain it. He was down to making YouTube videos trying to walk him through it. So Glenn Greenwald had to get a technician to set up his public-private key pair. And this is why the US government got so upset and they started taking relative members of his family and grabbing them in the airport and searching all their stuff, because they said, now we have top secret information being handled by idiots and being handled by a group of people who can't even keep a secret. Now that technician knows the key. Now your romantic partner who's going through customs and carrying stuff, and you're too stupid to properly handle the keys, and we're getting really bothered by this. And that's the problem. Public key encryption requires that the recipient is technically wise. This has proved to be an enormous, almost insuperable problem. And that's why Hillary Clinton had to send secrets through unencrypted email, because you cannot reach low-tech people with encrypted email. Anyway, so then there's hashing. Hashing has no key at all, and it's irreversible. Hashing just puts a fingerprint on a file so you can tell if it's been changed. So those are the 3 things you need: asymmetric encryption, symmetric encryption, and hashing. And that's what you use to encrypt data on the internet and everything else these days. So stream ciphers are ciphers that encrypt the bits one by one. You have this thing that generates a stream of apparently random bits, and you just XOR with the bit stream of the data. So you can make as much as you want. The most popular system is RC4, used in web, and also in many versions of HTTPS. Block cipher is the other one, where you have blocks of data, like 128 bits, and you encrypt that block, and then you have another block of data and another block of data. So DES uses block data and AES uses blocks. The problem with block ciphers is if your input data isn't an integral number of blocks, you have to pad it with some extra padding at the end. And that might sound like a trivial problem, but that turns out to be a very serious problem. All right, so you have an initialization vector. If the Microsoft made the same mistake many times. When I was in an escrow agency, in 1998, it was common practice to just we were printing checks to mail people money in response to lawsuits. We would take a database, we'd prepare it in like Lotus 123 or an early version of Microsoft Access, and then we would email it to the printer, and the printer would send it. We did that, and nobody knew anything about it until I started learning this, and I said, wait a minute, that stuff is not encrypted. This is messed up. I said, we should use Microsoft Office encryption and make an encrypted Microsoft Office document and email it. And so they did that, and everybody was happy. And years later, I learned Microsoft Office encryption was total crap, because Microsoft didn't use any IV. So they would just use one time they would use the simplest encryption mode where a block of data is scrambled with the key, and if another block of data is the same, you get the same output because there's no randomness anywhere. And so it turned out if you were to encrypt a Microsoft Word document with a key and then encrypt another Microsoft Word document with the same key, all you have to do is XOR those documents, and whole regions of it will turn into plain text. And Microsoft didn't know any better. They made the same mistake several times in their products because Microsoft Windows is not designed by one team. It's like the Frankenstein monster. Some other company makes something and Microsoft buys them out and patches them in, and buys them out and patches them in. So they keep making the same mistakes over and over because they acquire a company that made the mistake and put it in without noticing. Anyway, so you have to have an initialization vector. You add a random thing to each message before you encrypt it. And now if two messages are the same, the encrypted stuff is not the same. And the IV is not a secret. You can send it in plain text to the other end, but it has the result of preventing certain patterns at the output. And then there's cipher block chaining is the main method used, where you take the output of one encrypted block as the IV for the next encrypted block. This creates a somewhat random looking initialization vector for each block, but it does lead to some disturbing vulnerabilities like the padding oracle attack. Anyway, DES was the government recommended system to secure us. This was created with a very disturbing process. The United States government decided encryption was necessary in the 70s, and they put out a contest so people could submit their system, and IBM sent them Lucifer. Lucifer used a 128-bit private key, which would still be unbreakable by modern terms, but the NSA lowered it to 56 bits and called it DES. And it was never openly admitted, but it's obvious to everyone they did that because they could crack that. They weakened the encryption to something they could crack, and they assumed nobody else had the power to crack it, which was probably true in the 80s, and they made that the standard to achieve their goal, which is no bus. They have a backdoor, but nobody else does. They lied and told people it was safe when it manifestly wasn't. So there was a series of people trying to crack it until 1997, when people could totally crack a 56-bit key and exposed the weakness of this. So anyway, here's the modes of DES: electronic codebook, cipher blockchain, cipher feedback, output feedback, and counter mode. These are RFC standards for the internet. And these are different ways to use the encryption routine. Electronic codebook is what people call textbook encryption. This is where you have a block of data, you scramble it with the key, and that's the output. And if you have another block of data, you just scramble that with the key and get the output. So if you have two blocks of identical input, you will get identical output, which is a trivial problem. So that's how you get this. If you have this image and you encrypt it, it turns into that image. Now, you can tell this is not what you were hoping to achieve with encryption. I can still see the picture. The problem is this is a block of white, so it turns into something. There's another block of white, it turns into the same thing. That's the problem with electronic codebook mode. You didn't add any randomness, so you didn't really remove all the patterns. So this is textbook encryption, and as you can see, it's very, very limited. So what people use is CBC. Cipher block chaining is where you take the initialization vector and you add it to this and then encrypt it, and then you take the output of that is the initialization vector for the next one. So even though this is white, the thing you encrypt has something added to it that's different every time. So this turns it into just random stuff. Now all the patterns are gone. That's why this is the standard that everybody really uses. CBC is the standard mode almost all encryption uses these days for this reason. It's obviously much better than ECB. And all the other ones are similar. All the rest have some way of creating something that varies for each block to prevent those patterns. So single DES was the original one with the 56-bit key. The problem is since 1997, there have been computers got fast enough that they can really try all 2 to the 56 keys. So that's a brute force attack and you're hosed. There's no way to do anything except you get a longer key. So triple DES was the improvement. Encrypting it twice would not do any good because there's an attack called meet in the middle, where you take the point in the middle and approach it from the end and the start. So doubling something doesn't make it any stronger at all, but tripling it does. So triple DES does. You could encrypt it with 3 different keys. And this raises the effective security to 112 bits, which is very good, even unbreakable by modern standards. So we could still be using triple DES, and some people do. The only problem is AES is faster and more secure. So everybody has upgraded to AES unless they're using legacy equipment, in which case they might use triple DES. And if somebody's using triple DES, there's nothing really wrong with it. It's plenty strong. If they're using 1 round of DES, That is totally not strong. So IDEA is a public symmetric block cipher, another international alternative to DES. Had a 128-bit key, but a 64-bit block size, which turned out not to be so good. Anyway, the AES is the one that's recommended in America now. This is based on a system called Rindjael, and it has 128, 192, and 256 bits. They're all approximately equally strong, which you might not imagine intuitively, but the 256 actually uses less rounds of encryption, which kind of undoes the benefit of the longer key, but they're all very strong. All of them are effectively unbreakable. Nobody has found any way to get in them if you don't have the key. Rindjael is just the name of it. I think it's a combination of the two names of the authors. I think so. Anyway, then there's a bunch of others. What they did is they had a public race to do this. Everybody could submit protocols, and they had about 5 years of competition, and one of them was chosen to be the winner, and there are finalists. And so if you want to do business with the US military, the US government, then you use the approved standard. If you are more rebellious and you have a bad attitude, like most cryptographers in fact do, and you say the government probably wouldn't have approved it unless they hid a back door in it, you will never use the approved one. And what you use is the runners-up, which are the ones that were tested and found to be almost as good, but somehow not the one they approved. And history has justified this largely, that perhaps the government approval should be taken as a negative instead of a positive. So if you want to, you can use these. These are all the ones that are probably just as strong mathematically and did not pass through the NSA's hands to get approved. Yeah.
You go use like some standard software. You don't have this choice.
Of course, standard software is written by, basically, if it's a big business like Microsoft that wants to do business with the government, they just use the government standard. If it's some kind of little rebellious privacy enhanced phone service or something, then they probably use one of these because they're probably sort of hippie rebels. Those are your choices. And you know, as far as anybody knows, there's no backdoor in AES. People have looked and they've not found it. However, they have found backdoors in about 5 other systems that were approved. The most egregious was RSA, and they made their encryption, the NSA bribed them with $1 million to use elliptic curve cryptography of a certain kind as the default in their product, which they had absolutely backdoored, and it was Microsoft that found that. Microsoft researchers found the backdoor in ECC. So, I mean, that's suspicious. I would like to say that's suspicious. When I was a kid, the hippies were saying, oh, the government's putting LSD in the water and they're putting satellites everywhere and they're tapping everything. I said, oh, you guys are just paranoid. And the problem is that wasn't entirely false. They really did that stuff. When I worked at my escrow agency, one of the cases we had was unbelievable. It was the babies, the iron babies. The US government really did feed radioactive iron to pregnant women to see what would happen to their babies. Holy Christ, what do you think happened to their babies? But they did that. And I was part of the company that was giving them some money decades later to recompense them for that. I mean, this stuff, unfortunately, really does happen where the government is doing something horrible and lying about it, like they're doing with the migrant people from down south right now. Anyway, so the Rindjael algorithm is good, clean, fun. It works like this. You have the data coming, there's a state and a key coming in. Then you add a round key, you substitute, shift the rows, mix the columns, add another round key. You do that 9 times. It's just these fundamental transformations, 9 cycles of that, and the 10th cycle is skipping a step. That's all it is. It's just several rounds of doing these simple transformations, scrambling the bits. It's how you would make hash. You chop it up this way, mix it around, chop it up that way, mix it around, turn it over, chop it up this way. It's just scrambling the bits to take all the patterns out of it, but it's totally deterministic. So the other side where they have the key, they can totally reverse it all. And this turns out to be extremely effective. Nobody's getting an AES without the key. The problem is you have to somehow distribute the key. And somebody might be able to figure out the key from your distribution method, and that happens, and that's the problem. Anyway, Blowfish and Twofish are more symmetric block ciphers developed by a famous guy named Bruce Schneier, who gives very good talks and writes very good books. He's a wonderful guy, like Dan Kaminsky. He's one of the security celebrities. Get a chance to see his stuff, totally do it. He wrote these. They didn't win the finalists, but they're perfectly fine, and they're out there. There's a bunch of perfectly good cryptographic systems that didn't get the government stamp of approval, and they're available for use, and people do add them to some products. But most people stick with the standards, of course, because they want to do business with the government. Yeah.
the government still do it?
I don't know. I don't think anybody would care if you had other options. As long as you had an option that would use the standard technique, I would think. I don't think that would be too abusive. If they actually said, we're going to punish you for daring to use a strong algorithm. Skype, for example. Skype advertised they encrypted voice traffic and nobody could get it. And they said, we have a secret algorithm and nobody knew what it was and nobody could find it. And the head of the NSA actually offered $1 million to anybody that would crack it. And what happened is Microsoft bought Skype. And they totally let the government in, of course. And they found out that the secret algorithm was AES-256 that they were using in Skype. But you know, it's not illegal to make something using a forbidden algorithm, although it is probably illegal to send it to China. Anyway, so RC4 and RC5 are block ciphers with different sizes. They're around from RSA. And then there's asymmetric encryption. This comes from Diffie-Hellman key exchange, which is fantastically brilliant. If I make up a number and you make up a number and we multiply them by a secret number we never tell anybody and we send the product over the air, nobody can find the secret number unless they can factor the product of two numbers. And if I multiply 3 by 5 and I send 15 over the air, you can figure out that that's 3 times 5. But if I make a number 100 digits long and multiply it by another number 100 digits long, so the end is 200 digits, it's very hard to factor that long number into its component factors. So that's how Diffie-Hellman key exchange works, and that's how RSA works. The public key is the product of two numbers, and the private key is those two numbers. And you cannot find the private key from the public key because you cannot factor a long number. The only way to factor it is to try all the lesser numbers, and if it's a few hundred digits long, that's more calculations than you can ever do. So this is, in fact, very strong, and that's what's used in RSA. All right. So you have to have a one-way function for this to work. There has to be some operation that is easy to do and hard to reverse. Like you can multiply two numbers very easily, but you can't factor the product back into numbers. That's the one-way function for RSA. Something that's easy to go one way, so I can create the public key, but hard to go the other way, so nobody can find the private key from the public key. And there's a variety of these functions that can be used. So factoring a large number is the RSA one. Discrete logarithms is another one used by Diffie-Hellman and L. Gamel. And elliptic curve cryptography is another one with this sort of bizarre math based on ellipses, which again has an easy operation that creates a public key, and the reverse operation is very difficult. All of these are available. ECC is the one the NSA has been pushing for the last 10 years because the keys are much smaller, and therefore it's much faster. It costs 20 times less. So the ECC has been recommended for the last 10 years very strongly that we should all quit using RSA and use ECC. And so if you look at, say, my website, I have a secure website. Now, I got this for free because I use Cloudflare. Cloudflare is a set of reverse proxies. So when you go to my website, you're not going to my server. You're going to a copy of my page on the Cloudflare servers, or really a proxy in the middle, and they changed my HTTP to HTTPS. They put a certificate on it, and they did that for free. Now, this did this before there was a source of free certificates, which there now is. And the way they did it is they got cheap certificates, and the way they did that was they was hoping to. What's that? Oh yeah, no, not Komodo's all right. There's another one with a similar. There's another one with a similar name that's hosed, and someplace up here, I might be able to find it. Subject. I'm just trying to find my domain name because at one time I was sharing it with about 100 other websites, and I thought that was kind of fun. I don't know if I can find it anymore. Someplace should be my issuer. Well, maybe I'm not going to be able to find it in this crazy thing. Let's try Chrome. I hardly use Chrome anymore because of the privacy issues, but let's see if I can get Chrome to do this. I think Chrome makes it easier for me to find what I want to find. Okay, samsclass.info, Chrome, certificate, details. There we are. There we are. That's what I thought. This is somewhere in Firefox, but I can't find it. These are all the sites sharing this certificate. Rocket dates, safety from pests, samsclass.info, bhost Brazil. Like 100 domains are all sharing the same public key and the same certificate. And they're using ECC. If you look at the algorithm being used, someplace down here, there, it is elliptic curve DSA. So it's 20 times cheaper to do the cryptographic and decryption. So that made it cheap enough that Cloudflare could just give you a free certificate. They will let you share it with 100 people and use the cheapest kind of certificate. Mathematically, this is fantastic and better for mobile devices and Internet of Things and everything. And yet, 3 years ago, the NSA suddenly reversed course and issued a sudden declaration, everybody should abandon ECC. Drop it now, go back to RSA with prime numbers. And that's because of quantum computers. And so there are different ways to look at this. And again, it depends on how much you hate the government. From my personal experience of government proclamations like this is they would only say that when they are damn sure it's true. I think they have a quantum computer at the NSA. Other people say, oh, maybe they're just assuming it'll develop in 10 or 20 years and they're warning us in advance. I say, I don't think they would have done that based on maybe someday. I think what it means, and they usually are 20 years ahead of everybody else. Out here, we've got quantum computers that are early prototypes that don't really do much, but they're improving really fast. I think what this means is the NSA can already break this with a quantum computer. Quantum computers can cut the number of steps by the square root. So they can break AES 128 with 2 to the 64 operations. That's what quantum computers can do. So that means AES 256 will still be okay because 2 to the 128 is 2 more to do. Even a quantum computer can't crack AES 256. But the real problem with quantum computers is that these hard problems like factoring stop being hard entirely. With a working quantum computer, you could crack 4096-bit RSA quickly. And you could crack 1 million-bit RSA quickly. It doesn't matter how long it gets. The whole part where there's the hard problem, it stops being hard on a quantum computer. Now, the hardware to do that doesn't exist in the unclassified space yet. But everybody can see it coming in 10 or 20 years because prototypes exist and are getting better faster. And so they just need to get about 1,000 times smaller and cheaper and we'll be there. And everybody expects that in a decade or two. So all these public key algorithms are going away. So there's currently another competition going on from the National Institute of Standards to develop a post-quantum algorithm. There are 74 or 84 submissions. 10 of them have already been hacked. They're within the next 4 or 5 years and they will pick a new one. The current favorite is Google's submission called A New Hope. It is a lattice-based encryption scheme, and it solves the problem of learning with errors. So it is a little mind-boggling. I haven't quite got this project ready to give my cryptographic class, but I had to make a project. This system goes like this. You take the key is like 2 or 3 kilobytes of stuff. You encode the message in it, and then you add some randomness to it, noise, and you figure it out anyway, because it's the error correction process that is involved in the encryption. And the fact that there's some random noise included is what makes it unbreakable even on a quantum computer. So that is, and it has a sort of redundancy and error correction. So even though there's noise, you can take that out. And that process is somehow not susceptible to quantum speedup. So I did find some simple cases of it so we can play with it, but I haven't finished turning them into projects for my crypto class. And of course, that's all way beyond what you need for CISSP anyway. But that's the thing. You have to, these are the standards right now, and the standard everybody really likes is RSA. RSA is what people mostly use, the one prime numbers, and the ECC was temporarily seeming more cool, but then it kind of went back, and that kind of detail is probably not necessary for the CISSP test, but it is kind of useful to know. Anyway, and for the time being, RSA is fine, but people that worry about 10 or 20 years in the future are nervous about it, and they would like to use a post-quantum scheme, but there's no current reliable post-quantum scheme. So realistically, the thing to do is be aware of it and wait for the government to actually approve a post-quantum scheme before you jump to it. There's a few idiots like the cryptocurrency IOTA that jumped onto a post-quantum scheme and made up their own, and it turned out to be totally broken and hackable. Because, you know, you can't just make one of these things up in a week of work on your own. It's really hard to make an encryption scheme that's right. You really need the best minds in the world and several years of fighting to get a really good one. And whatever looks good to you is probably not really that good. So I wouldn't move to a post-quantum scheme yet. But when the government approves one, then it would be time to move. And it may be Google's scheme, and it may be one of the others. Anyway, so in RSA, You use symmetric keys for most of the encryption because symmetric computation is much, much faster, like 1,000 times faster. So the public key encryption is slow. So you don't want to encrypt the whole message with public key encryption. What you do is you encrypt an AES key and you send it with public key encryption, and then you send the rest of the message with AES encryption. That's how it works. So yeah, so you have a public key, like a public key I got from Google, that long 2048 bits. I can encrypt anything I want with that, and only Google will see it. So I could encrypt all my web traffic with that, but it would be really slow. So what I do is now I take a random 128 bits to make an AES key, and I encrypt that with the 2048 bit key, and I send that to Google. Now I have a private key, and they have a private key. Now we both encrypt with that AES 128 bit key, and the calculation is much faster. And it's really reasonably secure. I'm as secure as AES, and I'm as secure as RSA. Of course, if either one of them were broken, I'd be hosed. But as far as anybody knows, both of those are strong routines, so nobody's getting in there, at least not by recording the bits on the wire and doing a mathematical transformation. Now, there's plenty of ways to get in. They can just put a virus on my machine and get a keylogger and get the data before it's encrypted, or put a camera in the room to watch me. You know, there's always a way, but they're not going to get it off the wire. That's all you can accomplish with encryption, is blocking one attack so they have to use another attack. That's all any security measure can ever do. Anyway, hash functions are just to put a fingerprint on a file so you can tell if it's been altered. There was MD4. MD4 is Microsoft's password hash because they defined it in 1993 before MD5 had been written. It's fantastically weak, and for some ungodly reason, Microsoft never updated it. I've humiliated them in publications and conferences for years about this, and I haven't been able to make the move yet. So if you want to crack a Windows password hash from you can literally do it 1,000,000 times faster than a Mac or Linux hash, because Microsoft uses an algorithm that's 30 years out of date for no apparent reason. But anyway, MD5 is the standard used by almost every product. It became very popular, but it's not secure anymore. SHA-1 is much better, but there was a SHA-1 collision discovered by Google about a year ago, the very first one ever. And so SHA-1 is no longer perfect, although it's very good. And so most people are moving to SHA-2 and SHA-3, which, as far as anyone knows, are completely unbroken. So if you find a file with a SHA-2 fingerprint, there is no way anybody will ever find any other file with the same fingerprint, as far as anybody knows. And all right, a collision is if two files have the same hash, but they're not identical. That should never happen. In principle, it happens, but they should be so rare that you can never find them. But it turned out they found them for MD4, they found them for MD5, and now they found them for SHA-1, so people have moved up to SHA-2 or SHA-3. All right. And I'll get rid of Chrome and go back to here and find cahoots, and they will be cahoots 4B2. Okay. Or B2. Oh, okay. You got it? Okay, good, good. Well, it's a free service. Sooner or later, somebody's going to get tired of running it. They're beginning to be more annoying with pop-ups saying, gee, why don't you pay us some money? So I might even pay them some money sometime, but I haven't done it yet. I don't see very many ads on the screen either, so this is obviously somebody's lost leader. And I don't know, maybe Google will buy them or something. I don't know. And it's pretty cool right now, but it can't last forever without getting any money. That's my evil capitalist interpretation. What's the strongest system on this list? One-time pad is, as far as anybody knows, a perfect system. The only problem is key distribution. But if after you distribute the key there, nobody is figuring out that message without the key. Which one uses no key? Hashing is not intended to convey information or hide information. It's just putting a fingerprint on the file. Which cipher encrypts bits one at a time? Okay, that's a stream cipher. Which mode preserves patterns in the input? The electronic codebook mode is the one where the apple, you can still see the apple, where each block of input is looked up and an identical block of input results in an identical block of output, which is also called textbook encryption. This is what you'll do if you take a math course and you learn the encryption algorithm and you don't worry about how to actually do it. If you just apply the encryption algorithm naked, you have this, which is not much good at all. This is why industry people always sneer at academic stuff. I heard cryptocurrency Zcash is the privacy cryptocurrency, and the math is very impressive. And there's a guy there who didn't go to college at all, who made the essential protocol. And he said, I have learned every time I read an academic paper, I have to rewrite every line of code. Never use college academic code in anything because it never works. They don't know how to do it. They don't write code that will parallelize and scale and be secure. They make a quick and dirty prototype. And he said, I've learned that those guys have no idea how to really do anything. And this is the thing. You have college, there's book learning, and there's the real world. And this is the kind of thing. Go to college, they'll teach you ECB, where you're worried about how the algorithm works. You use that in the real world, you're making a mess. Anyway, what's the weakest scheme on this list? DES, of course, that's the one that's actually broken, the official government standard, until about 98 or so. It's the only one of these that's totally broken. The others are perfectly fine. Which one is popular on mobile devices? ECC is the one that saves power. And by the way, if you make the key much longer in ECC, it's still considered reasonably safe. And they've only proven that there was a backdoor in one of about 8 ECC protocols. So some people feel like you might as well trust the rest. How bad could it be? And other people just have a bad attitude. Nobody really knows except people with clearance who presumably aren't blabbing, except for Snowden. And he didn't happen to blab about this. Although I have heard rumors that there is another Snowden in the NSA leaking stuff out. Supposedly, even beyond the shadow brokers, there's more secrets leaking out, but nothing so dramatic yet. Anyway, Robert and Jane and B. Robert and Jane and B. All right. Anyway, so let me see where we are. The cryptography tends to deaden people, and there's quite a bit left. I think we should take a break before proceeding. So 185. So it's 225. Let's take 15 minutes, pick up at 240. Yeah.
I can't enroll in.
Oh,